So let's review the acid-base short quiz, especially the first two questions. I want to show you how these two questions are not all that difficult, although I had a lot of students who did not get these right. So let's talk about these and let's go over them. Number one, what is the hydroxide concentration of a 0.13 molar HNO3 solution? Well, the first thing you have to recognize is that we're dealing with a strong acid. Now you say, Mr. Grodsky, how do I know it's a strong acid? Well, at this point, you should be able to look at your Ka table, that famous table L, and see the strong acids up top there. So let's go there. There will be some courses that will make you know your strong acids, but just working from a table, a Ka table that I gave you here, strength of acid table, you can see that the Kas are very large for acids on top. They're so large because Kas, of course, are products over reactants. Coefficients become exponents, and solids and liquids don't apply. They really represent equilibrium constants. They are equilibrium constants for the dissociation of acids. So if the Kas are large, it's because it's products over reactants. There's a lot more of these guys. So a strong acid completely dissociates, as we've talked about already. Therefore, its Kas are numbers approaching probably infinity. So in this case, in this table, okay, these guys right here are your strongest acids. They're the top 5 acids. Now, we generally have 2 more that we introduced in AP, but from this table that we're working from, we'll use these 5 acids as our strong acids. And I know that because, well, my Kas are extremely large. After the top 5 acids here, we have weak acids where the Kas are less than 1. Remember, it's products over reactants, the concentration of the products over the reactants. And if you've got a lot more what? Products than reactants, because these guys essentially dissociate and go forward, the Kas are larger. So clearly I gave you a strong acid that completely dissociates. And this strong acid is called nitric acid. It's a strong acid. Now again, writing that out, that means that the HNO3, and the H in front kind of gives it away, dissociates into a proton and the conjugate base NO3 negative. Now it completely dissociates. So if I know the concentration is 0.13 molar for the HNO3, it's going to be 0.13 molar for the H+. Well, why? Well, we're going to use up all of the HNO3 to produce this. Because it's a 1-to-1 ratio, all of the HNO3 will become H+. So if this represents all of the HNO3, this will become exactly that number. And it only works if there's complete dissociation. And you can only do this the way that I'm going to solve this problem if it completely dissociates. So knowing that this number is the concentration of the acid and it's also the concentration of the proton, I now have the H+ ion concentration because of complete dissociation. It equals 0.13 molar. Now they wanted in the question, what is the hydroxide concentration? Well, I already know something. I already know that Kw is equal to the H+, or the H3O+, if we're dealing with hydronium ions, times the hydroxide. That's something we've already established from the autoionization of water. Kw we know is 10 to the negative 14. We know the H+ now, because of it being a strong acid and completely dissociating, we know that this value is 0.13. So what's my hydroxide? My hydroxide is my unknown. So solve for my hydroxide. All I have to do is take 10 to the negative 14 and divide it by 0.13. That's all you had to do. Some of you guys are trying to solve for, I don't know, Nobel Prizes in different types of equations you were building. So, so I go basically 10 to the negative 14 divided by 0.13. And all I get is 7.69, and I guess I'll stop with 2 sig figs, 7.7 times 10 to the negative 14. And that is equal to my hydroxide ion concentration. which is tiny. Well, why? Well, this is a small number, which means this number must be a huge number, and it is, comparatively speaking. Okay, usually we're dealing with 1 times 10 negative 3, but it's 0.13. That's 1.3 times 10 to negative 1. So it makes sense that this number is going to be very small, very acidic. Now, of course, I could have done this another way. How could I also have done this? I could have said, okay, I could say, knowing that this is my H+, I could have gone, okay, negative log of this to get my pH. So I can do negative log of my 0.13 solution, and this would have given me a pH to be let's write that neater, my pH to be equal 0.887. People say pH of 0.87, that doesn't sound right. What do you mean? It's a real number. It's between what? 0 and 1. Definitely a possibility. Okay, so that's the pH of my H+. Now I was looking for the hydroxide concentration. So what I could also do is say, okay, well, 14, which is the pKw, minus 0.887 is going to give me my pOH. So when I minus that from 14, I get my pOH to be negative, equal 13.11 or 11. That's my pOH. Okay, because guess what? My pKw equals my what? pH plus the pOH. Now why is it plus? Why am I adding these? Because when I multiply exponents, I add them together. And these pHs are exponents, base 10. All right, so now that's not the answer though. They want the hydroxide concentration. So what do? I can do 10 to the negative 3.11, and that would give me my hydroxide. So when I do 10 to the negative 13.11, I get my 7.7 again, times 10 to the negative 14. Either way, you want to take it and make it into a pH, subtract from 14, get the pOH and do 10 to the negative x to go back to the real number. Be my guest, it doesn't matter to me. Or you can say, listen, I just realized that this is the H+ ion concentration, so all I got to do is solve for the OH this way. It doesn't matter. Either way, you get the right answer. But I don't think this was a big deal. We've had these problems before. Okay, we went over these problems. And I believe that pH propaganda ditto. Yeah, nice name. But it's a good review. And if you didn't have a quiz that made you think about this, there's something you probably would have gotten right on a test that's essentially coming up. All right, now number 2 is an easier question in my book that people had just as much difficulty. What is the pH of a 10.2 molar solution? All right, well, my friends in chemistry, this is a strong base. You say, well, how do I know it's a strong base? My friends in chemistry, you know solubility rules. We know that sodium, or all group 1 ions, K+, okay, rubidium, cesium, all of our lithium, all of our group 1 ions are always soluble because these ions tend to be pretty big and their charge densities are very small. So any salt with a group 1 ion is going to be very soluble. So that includes the hydroxide. So NaOH completely dissociates into the Na+, which is going to be a spectator, and a hydroxide. So my friends in chemistry, the only way that you could have done this is realize that this concentration is the concentration of this special salt called a base because it's got a hydroxide polyatomic ion. So if it's 10.2, just as I said before, if there's complete dissociation, all of this will become the Na+ and hydroxide. Because there's a 1:1:1 ratio, then therefore all of the NaOH will become Na+. So this will become plus 10.2. And so the hydroxide, okay, and that's really the one I'm after. So all of the NaOH becomes the hydroxide. Now, of course, it makes 10.2 molar solution of Na+, but that's a spectator. It doesn't affect the pH. This is what I'm after. So this is what, so again, dealing with a strong base, the concentration given is really the concentration of the what? Of the hydroxide. And now what do they want? They wanted the pH. Well, the first thing I'm going to do is do a negative log of this to put the entire number into a exponent. And what I do is I take my 10.2 or negative log of 10.2 in my calculator, and I get essentially -1, which bothered some people. -1.0. And by the way, this is my POH. How do we get our pH? Well, same as before, because I know the KW, or like we did before, PKW, which is going to be the negative log of the KW, is 14 equals the pH plus the POH. Because of that, I'm going to take my 14 and I'm going to basically subtract -1.0. Now, when you subtract or have two negatives, as you've learned in math, it becomes plus plus. So the answer to this is you now have a pH of 15. All I did, party people, knowing that 14 equals what? Let's do that in the color so it stands out. So we know that 14, which is the pKw, equals the pH plus the POH. Well, guess what? I had the POH. I know 14. Solve for pH. So 14 minus the POH gives me the pH. It just so happens my POH is negative and my pH is 15. Now I know that bothers some people. I say, how can you have a pH of 15? Very easily. Think about this for a second. If I have a 10 molar, let's make these numbers easy to think about. All right. Let's talk about a 10 molar solution. Let's wipe this away a little bit. So if I take a 10 molar solution, think with me for a second. What is pH? Remember, it's 10 to the negative 14, which is the KW, equals the H plus times the hydroxide. So we know these two numbers have to always multiply up to this number. That's the equilibrium constant called KW. All right, well, my friends in chemistry, if my hydroxide concentration is 10 molar, which is essentially what it was, and we can have a 10 molar solution. I mean, there's a limit to it because of solubility. 10 isn't 10 really 1 times 10 to the 1? Absolutely. Now, we're used to putting small numbers here, but this happens to be a very big number. So what must my H plus be in order for this to equal 10 to the negative 14? Well, 1 plus what negative number gives me 14? Well, 1 times 10 to the what? Negative 15. And remember, pH is about the what? pH is about the negative log of the H plus ion concentration. So if this number is greater than 1, it'll drive this value beyond negative 14. So yeah, pH of 15 is very possible. Now we can't have an unlimited pH because when it comes to sodium hydroxide, there's a limit to solubility. Could there be a pH that's less than 0? Since we're talking about it, yeah, let's talk about it. What if I was to give you an acid that was 10 molar strength? And you know, hydrochloric acid, full strength is 12 molar. So this is a possibility as well. So if I give you a 10 molar solution, and now 10 molar is 1 times 10 to the 1. So let's write that there. So 1 times 10 to the 1. Notice it's greater than 1. What must this number be? Well, of course, this must be 1 times 10 to the negative 15. That's a 15. And that equals, of course, 10 to the negative 14. However, when we do the negative log now of my H plus ion concentration, negative log means we're going to take the what? The exponent, base 10, now the one in front, so it's 1, and we're going to make it negative. So this becomes negative 1.0 pH. So we can have pHs that are negative and pHs that are greater than 14. Whoever taught you 0 to 14, okay, is not telling you the true story. So we can have pHs smaller than 0. -1 is a definite, and it does exist, and pH is above 15. Okay, so in any case, those are the two questions that people had some trouble with, and I hopefully can see that those are no big deal, and we covered these questions. These were on our first or second worksheet. In any case, looking back down on the third question that people had trouble with, all right, if you look carefully from table M and looking at our indicators, we know that the yellow means that we are at a what? At a pH that's less than 8. Being Brome Crystal Green being green means we're between 3.8 and 5.4. So now we know that the pH is less than 8 and between 3.8 and 5.4. Litmus went red, which means it's 4.5 or lower, and methyl orange went yellow, which is 4.4 or greater. So because of these indicator change, clearly, okay, we're between 4.4 and 5.5. And I want the approximate H hydronium ion concentration. I wasn't asking for the pH, I was asking for the actual value. So we've got the pH to be 4.4 or 4.5, and what I did to go from a pH back to a real number, we do what? 10 to the negative x, as I've been doing before. If I want to go from a POH back to a regular, 10 to the negative x. So all I did, party people, was take 4.5, do 10 to the negative 0.5. Okay, this is the range, it's on the negative pH. And this gives me my what? My actual concentration. So if you notice, it goes from 4.4 to 4.5. So we go from 3.16 times 10 negative 5 to 3.98 times 10 negative 5. I basically said that you could give me any answer in between here, because the pHs that gets narrowed down by these colors, by these indicators, we narrowed it down between 4.4 and 4.5. I did 10 to the negative x, or 10 to the negative 0.4, 10 to the negative 4.4 to get this number, 10 to the negative 4.5, 10 to the negative 4.5 to get this number, and this was the range that I accepted. The rest of this was very simple. Most of you guys did a great job in figuring out the conjugate acid-base pairs. Some people still messed up on the conjugate. Conjugate means you have to have the what? The same chemical plus or minus the what? H's. And also, if you lose an H, check out your minus signs. You have to have those signs. So the conjugate had to be the same. Some people messed up their acid and bases, okay, and they flipped that, and I only marked you wrong once. The rest of these questions are self-explanatory. Number 7, who is a better electrolyte? Who breaks apart into more free ions? My friends, in chemistry, it's the one with the larger Ka. Why? Larger Ka, if this is an acid, is going to break apart into more undissociated ions. So this was essentially an easy quiz that people thought the 2 top questions were tough. Now let's continue and review with the homework. Okay, so if I continue on with the homework, let's do so. Okay, in the homework, I find the pH of 0.13. Okay, so for the first question, the question was, what is the pH of a solution that was 0.13 molar HF? That was the first question. And the other question was, what is the pH of a 0.13 molar Hbr? Now these 2 questions look very similar. In fact, it's essentially the same question, I believe, as question 2 in your quiz when you're dealing with a what? Strong acid. So my friends, when I'm dealing with Hbr, let's do this one first. Hbr is a strong acid. How do I know? I've got myself a table that tells me Hbr is on top of the others. It's got a very large Ka. It's one of the top 5 acids in this chart. It has a high Ka. More products are favored. So clearly, I've got a strong acid. I have a strong acid. So what we do here is we're going to do this one first, and this is the easiest. Because it's a strong acid and completely dissociates, guess what? I know the concentration of the acid is what? Equal to the concentration of the protons. So it's equal to 0.13 molar. So gosh, all I got to do, my friends, is do the what? negative log of 0.13, which is the H plus ion concentration. That is no big deal, unless it is. So I take a negative log of 0.13, and I get, wow, lo and behold, I get 0.88. Now I have 2 sig figs, so 0.89. And that's my pH. Wow, that's so tough. Mr. Growski, this stuff is so difficult. Come on! All I got to do is do negative log of that, because that is the H plus ion concentration. The pH is the negative log. So obviously, the second question I gave you was just like your quiz. And I would think very simple. The first question, okay, well, is a little more difficult because we have 0.13 molar HF. I'm looking to solve for the pH. And my gosh, I know that this is not a strong acid, no matter what certain TV shows or TV movie shows say. HF is a weak acid. It will not, okay, as some shows on TV or movies that show you, it will not basically corrode a ceramic tub and dissolve it. So in any case, the point being is I take my HF and we got to go to the table. So go to table L, and we see that HF is not a strong acid. So all I'm going to do, I'm going to look it up, and I see HF is a weak acid, and I see it has a Ka of 3.5 times 10 to the negative 4. I'm going to need that, okay? So I'm going to write that down, 3.5 times 10 to the negative 4. All right, so my Ka is equal to 3.5 times 10 to the negative 4. That's an important number. We'll see in a second. All right, so how do we deal with this problem? Well, I'm going to write the reaction out. HF is going to dissociate into a proton and its conjugate base. Keeping the water out of this, I could have the water with the HF and make H3O+. It's synonymous. It doesn't really matter. So we're going to just keep it very simple. And that doesn't make a hydroxide. It makes a fluoride ion, which is a conjugate base of the hydrofluoric acid. Okay, and we're going to make something called an ice table, because I have to use my equilibrium, okay, value, not large, it's not completely dissociating. This does not completely dissociate, so I cannot use this number and do a negative log like I did with the first one. I have to figure out how much does this dissociate. So we started initially, the I means initially, with 0.13, and guess what happens? Oh, well, initially, before something happens, we have initially 0 and 0. We say, well, why is it 0 and 0? Because we're starting with this theoretical HF, okay, before it starts to react and make an equilibrium. Notice I added a double arrow there because this is an equilibrium constant. Remember, it's a KEQ for this reaction. We call it Ka because it's an acid reaction. And we say it's with fancy pinky up, a fancy name for that equilibrium constant for acids is acid dissociation constant, whatever. So our initial concentration before equilibrium is established is 0.13 molar. Now, what's the change? Well, this is going to work always toward equilibrium. Okay, as we dealt with, we talked about before, reactions always move toward equilibrium. So this is going to have to go down. So it's going to go down by some value called x. I don't know what it is. We're going to try to find that, but it's something. Now, whatever this loses, guess what? This has to gain. It's plus x. And this is also plus x. The reason why it's the same x is they're stoichiometrically the same. It's a 1-to-1. So whatever this loses, these gain the exact amount. Has to be. Now, at equilibrium, it's going to be 0.13 minus x, and 0 plus x will be x, and this will be x. Okay. Now, what do we do from here? Well, we're going to have to plug this value into our equilibrium expression. Sounds like fun. Oh, it is. So let's have some fun. So KEQ is equal to the products over reactants. Well, the products here are the H plus ion concentration and the fluoride ion concentration over the what? Over the HF, the undissociated acid. And well, guess what? We know that KQ or Ka, we know the value. What's the value? The value is 3.5 times 10 to the negative 4, sorry. And what are these values? Well, we've got x, right, and x. So we put the x's in. X times x over 0.13 minus x, but I'm gonna leave this x out. I'm gonna approximate this away. So why am I approximating it away? Well, I know the Ka is small. What does that mean? If it's less than 1, who's favored? Of course, the reactants are favored. So this barely goes forward. That means this x is going to be insignificant compared to this. If you put this minus x here, equaling 3.5 times 10 to the negative 4, you would come up with a what we call it, quadratic or a binomial. And you need the quadratic formula to solve for it. And that would take some time and effort, and you'd go through all of that, and you would see that your answer would be just the same as the one if we approximated this away. We're going to say that this little negative x is insignificant compared to this big number. Therefore, there's no need to go through all of that. So we solve this. X squared equals 3.5 times 10 to the negative 4 times 0.13. Bad planning on my part. So we're going to times that by 0.13, just doing some algebra. And let's do that. So we take our calculator, as opposed to doing long-handed, 3.5 second e to the negative 4 times 0.13. And I get this number to be 4.55 times 10 to the negative 5, and it equals x squared. To get rid of the x squared, what do? We square root both sides. My gosh, math is happening. X equals what? Well, it's the square root of that number. And I get x is equal to 0.0067. Small compared to this number, isn't it? And what is x? X is these guys. And guess what? I wanted the pH. Now I know. Notice something. In the other problem, we took the exact number, 13. We did negative log of that. Now what are we doing? Now we have to take a number far smaller. Why? Because it barely goes forward because it's a weak acid. The small Ka is telling us that. So last but not least, they wanted the pH of this. So you do what? Negative log of your H plus ion concentration, which is that's what this is. So negative log. And what I get a pH, okay, that is 2.17. And I guess we're doing 2 sig figs, so 2.2. Notice something. Equal concentrations. They were both what? They were both 0.13. This one gave me a concentration of what? Of 0.89. So the Hbr gave me what? 0.89 pH, pretty low, less than 1. And the weaker acid for the same concentration gave me 2.2. Okay? So you can see that the weaker acid has a higher initial pH than the stronger acid. But you need to understand that the first part here, okay, the first one, or the second, the Hbr problem, I should really say, didn't need an equilibrium to solve because it was complete dissociation. So that's the key to the homework last night's.